Hello dear students, the next topic of this lecture series based upon statistical physics is thermodynamic potential. Thermodynamic potential is also called Gibbs free energy, and it is just the difference of heat function W and product of temperature and entropy. Mathematically, this thermodynamic potential is represented by phi, and mathematically phi is equal to W, which is heat function, minus T, which is temperature, and S is entropy. So from mathematical definition, you can write it a qualitative definition. It is easy to do. Since this W, T, and S all are state functions. So phi is also a state functions. What are state functions? They depend only on the initial and final positions irrespective of the path followed by them. Next is physical significance of thermodynamic potential. By definition, phi is equal to W minus Ts. Now change in phi during any process from position 1, let it be phi 1, to position 2, let it be phi 2 is. Small change represented by del, so delta phi is equal to phi 2 minus phi 1. Value of phi at final point minus value of phi at initial point. So by definition, phi 2 is equal to W2 minus T2 S2 minus similarly phi 1 is equal to W1 minus T1 S1. So on rearranging and grouping the similar terms, W2 minus W1 minus T2, I have kept minus common, T2 S2 minus T1 S1. So W2 minus W1 is small change which is represented as W, del W minus del of product of temperature and entropy. So for isothermal process, this temperature T1, T2, let it be T remains constant. For isothermal process, temperature remains constant. So this T can be taken outside this delta, which represent a variation. Now change in heat function during a process at constant P is, we know that what is heat function? This is del W is equal to del E plus P del V. So putting equation number 2 into 1, so 2 into 1, this is 1, this del W can be taken from equation number 2. So this become equal to del W. So del E plus P del V, and this is here already here in equation number 1 minus T del S. So what is T del S? We know that del Q is equal to T del S according to second law of thermodynamics. So on rearranging by keeping this minus common, minus sign common, this become minus bracket del Q minus del E minus P del V. So del phi becomes equal to minus of these all thermodynamic quantities. But according to first law of thermodynamics, this del Q is equal to del E plus R max. This is maximum work done, and it is maximum work. Why it is called maximum work? Because in isothermal condition, the work done is maximum. But it is constant. The work done is maximum. So del Q is equal to del E plus R max. This is work done, maximum work done. Next is putting equation number 4 into 3, we can rewrite it. This del phi comes out to be, this term becomes equal to R max minus P dV. R max minus P dV. Hence reduction in del phi is maximum work done by the system. Maximum work done by the system, and this is reduction in phi minus. So hence reduction in phi, which is represented by minus, is the maximum work done by the system, this R max, minus the work done by the pressure forces, which is P del V. This del phi is calculated at constant temperature. We have seen that we have considered the work done in isothermal process, and we have also considered heat function which is taken at constant pressure. So the thermodynamic potential or Gibbs free energy, which is represented by phi, is the maximum amount of non-expansion work. This is other than this PdV, other than PV type at constant temperature and constant pressure that a thermodynamically closed system can produce. So this is non-expansion work, and this is maximum work done by the thermodynamically closed system. Next is total differentials of thermodynamic potentials. By definition, phi is equal to W minus Ts, and we know that heat function is also defined as W is equal to E plus PV. So putting equation number 2 into 1, phi become E plus PV minus Ts. On differentiating it, so d phi is equal to dE plus PdV plus VdP. Differentiating it by parts, minus, again differentiating it by parts, minus TdS minus SdT. Since d is equal to dQ minus PdV, and this dQ is equal to, we know that TdS, so TdS minus PdV. Putting equation number 4 into 3, putting equation number 4 into 3. So this is equation number 4 and this is 3. So d phi is equal to dE, which is equal to equation, according to equation number 4, dQ minus PdV. So d phi is equal to TdS minus PdV plus VdP plus PdV minus TdS minus SdT. So we can simplify these terms on right hand side. So TdS plus and TdS minus, they will cancel out, and PdV minus or PdV plus, they will also cancel out. So we are left only with two terms. First is VdP and second is minus SdT. So d phi is equal to VdP minus SdT. This is total differential of thermodynamic potential. Let's discuss about its differentials. We know that differential of Gibbs free energy is equal to VdP minus SdT. We have done it in earlier slide. Now on differentiating it with respect to P, keeping temperature constant. So for it, this second term will become 0. And this curly phi upon curly P at constant temperature comes out to be V. Again, similarly differentiating with respect P at constant, with respect T, sorry, this is with respect T at constant P. For constant P, this first term will become 0. So we are left with curly phi divided by curly T at constant pressure comes out to be minus S. So these are two differentials of thermodynamic potentials. Now what is the difference between Helmholtz free energy and thermodynamic potential, which is also called Gibbs free energy? What is the basic difference between these two terms? Because both terms represents the work done, maximum work done by the thermally isolated system. But there is a small difference between these. Now Helmholtz free energy del phi gives the useful work that a thermally closed system can produce. This gives the useful work other than PdV. Non-expansion work. This gives the non-expansion work which is available in the system. And del phi gives the maximum work that can be extracted from the thermally closed system. This is the maximum work that can be extracted from the thermally closed system. We have seen that F is determined for systems at constant temperature and constant volume. Similarly, this phi is determined for systems at constant temperature and constant pressure. So in both cases, temperature is constant. We have considered in both cases thermally isolated, thermally isothermal systems. But here it is V constant, here it is P constant. The third difference is that F model requires that V be constant, which restricts its usefulness. But phi models requires that PV constant, and this constancy of pressure is achieved or obtained in normal conditions, which can be achieved easily. So pressure is constant always when we work with the system or body or the surroundings. Pressure is naturally constant. So we have do not put extra effort to keep it constant. Fourth point is same, that del F when it becomes equal to when it becomes negative or del F is less than 0, then it represents that your chemical reaction is spontaneous or feasible. So it indicates the feasibility or spontaneity of the chemical reactions also. Similarly, when del phi is negative or del phi is less than 0, the chemical reactions are also spontaneous or feasible. There is no difference in fourth property of del of phi and f. Thanks for listening and watching.